Good morning, everyone. My name is Jianfeng Jia. I'm very happy to be here to present our work. Our paper name is From a Rhythmic Approach to Interactive Analytics on Large Data. This is a joint work with my two advisors, Chen Li and Michael Carey. We are living in a big data era. There's a huge amount of data that generated daily or even every second around us. And in order to understand the big data, the data visualization tool is an indispensable tool to help users to quickly draw insight by looking at the readable report and figures. In a very high level speaking, the visualization process will consist of two steps. The first step is the data processing step, which is convert original data into the required format. Usually that is aggregation result or a small fragment of the result, which is small enough that can be stored in the memory. And then can utilize some of the front-end libraries like D3 and PowerView to configure what kind of graph we want to show on the front end, so that user can easily interpret the graphic result. Follow the same design principle, we designed a visualization platform in UC Irvine, and then we want to interactively visualize 1 billion tweets. In the left of the figure shows the snapshot of the user interface. Basically, user can type any keywords, and then the system is able to give you the spatial and temporal aggregation result for the number of tweets and mention the specific keywords. And then the left part of the the UI shows the sidebar shows the number of the related hashtags and sample tweets. Furthermore, user can interactively play with the result by drag and drop in the graphic user interface by slicing on different temporal intervals and also zoom in and zoom out to show the different granularity of the result. And the entire system we set it on a small cluster, which is using the very commodity hardware. It's on a Intel nuclear machines, which only cost less than $4,000. Our target of these applications, we want to achieve the interactive user experience by visualize a large amount of data. So under the hood of this front end, we store the data inside the R3DB. And then, in order to provide, to further optimize the response time, we implement a middleware called Cloudberry. And then the most important weapon of the Cloudberry is using the materialized views to speed up the query performance. One thing we need to mention is that this view management or is automatically built by analyzing the query workload. However, the latency issues haven't been completely solved, because it's always the case that the views cannot help the new queries. And especially in this case, we need to send the query directly to the database. Due to the large amount of data and the nature of the aggregation queries, scan nature of the aggregation queries, it's gonna take a long time to finish a query on a small cluster. So we borrowed the idea of the progressive computing in the industry. So instead of let user to wait for the entire result to come back, we want to deliver the result progressively so that user will not get bored during the waiting. And then the partial result actually can convey some useful information to make that user to make quick decisions. In order to achieve this partial result delivery, first of all, in the middle layer, we need to we need to split the query into small pieces, and then we call these techniques as query slicing, which is split the original query into a sequence of mini queries. That each of the mini query has additional range conditions on a given slicing attribute, for example, the time dimension. And then the size of the range conditions plays important roles to determine the mini query response time. As an example, suppose the middleware get a request which asks for the by state aggregation result for the number of tweets and mentioning election. What the middleware can do is we can split the query into we can make 3 mini queries. The first mini query is attaching the September to December time ranges, and second is attached with April to September time predicate. In this way, we are expected the underlying database can visiting less amount of data, so that the query response time of these mini queries is much faster than run the original query entirely on the entire data set. So the next question is how to choose the size of each of the mini queries. The naive solutions as actually implemented in many places is fixed length slicing. So, however, the problem of this approach is it is very difficult to fix that length. This is mainly due to 2 factors. The first of all, the different query has different performance numbers, and then the database performance can fluctuate, especially under the case that multiple users are using a system and then there's multiple query runs in the database. And another important fact is if we slice the query on the time dimension, we are expected the distribution of the records on the other dimensions may not uniform distributed. For example, we have the election data, number of, for example, the figure shows the daily distribution of the tweets that mentioned in election. You can see there clearly there's a huge spike around November 8th, where the election actually was happening. After that, all the heat of this election tweets is decreasing. So we, as a illustrative example, we show the user experience of the fixed length slicing. As we can see that the query result delivery code given to the front-end UI is fluctuating. So sometimes slow, sometimes fast. It means either because of the distribution of the elections, and also could be affected by the underlying database performance. So what is the good slicing schedule? So compared to the original schedule, which doesn't show the user, for example, in S1, we just run the query as it is without any slicing. The user cannot get any update before the query finished at 6 seconds. And then query slicing, if we're using fixed time slicing, fixed length slicing could possibly achieve a better responsiveness. But for example, the schedule S2 is split the query into 4 pieces. The first query may be run very fast to return at the first first second. Then the schedule 2 maybe runs 3 seconds, which given the user very irregular updating user experience. What we want to achieve is something like S3, so user can get an early update as soon as possible, and then user are expecting to get a result on the front end, expecting to refresh its UI in a regular pace, not too fast, not too slow, for all the queries. So In order to measure the schedule cost, we defined we want to balance between the total running time and the smoothness of the result delivery. So total running time is the total time that scheduler is spending on the scheduler has spent on the to solve the entire to complete the result. And smoothness is evaluate how the result is being delivered to the end user. It should not be too fast and should not be too slow. So as a middleware, if there are two different cases, for example, when the user gives an update in phase P, the milestone to receive the result is fixed as UI-1 and UI. So for the first case, if the mini query runs slower than runs faster than the expected deadline, we can just reserve the result and give it back when the time is coming. In another case, for Q1, even he has longer time limit to finish a query, but if he runs out of time, the middleware can do nothing by just can do nothing and then have to give the cause this unsmoothness, cause this irregular update to the front end. So in this case, we want to punishment this query result delivery by giving a penalty to the cost. So the total cost functions consist of the total running time and the penalty given to the irregular updates. So as we can see, the previous query response time is actually affecting the next query. So we present a DROM, which is an adaptive framework to adaptively slice the mini query based on the query performance, the mini query performance. It consists of the three main components. The mini query generators generate used estimation information given by the estimator to decide the range of the next query. And then once a query has been formed, the mini query executor will run the query and collect the result and send to the downstream operators. At the same time, the mini query executor will collect the runtime statistics. For example, what the range of the size of the range and what is corresponding running time. And then those statistics is given to the estimator to update his estimation models. Specifically, we are using the regression model to capture the relationship between the size of the range and the total running time, the mini query running time, and also we are using the uncertainty model to measure the confidence of this regression functions. Next, we just go through an example to illustrate how the DROM framework works. First of all, we assume that each query's statistics is independent because each query can have different selectivity and the database can fluctuate from time to time. So assume that suppose that the expected updating rate in the front end is given is updating get one result every 2 seconds. And then we assume that the user, the administrator can give us we assume that there's a minimum query range, which could be an experience number that can start with. So suppose that is the minimum range is 1 day. We start this query as last the request slash the query using a 1 day time range, and then if the query is being finished within 0.5 seconds, we can see the next time limit for the Q2 is extended to 3.5 because they already have one result reserved, and then we only need to return result at time of 4. So since we do not have enough information for Q2 and Q3, what we did is just simply double the range of the predicate, double the size of the range predicate to collected enough information. Now, for the start from the first query, the statistics model start to play the role. For the L4, which is the deadline for Q4 to finish, that is 4.2. Then how should we choose the size of Q2, Q4? Based on our statistics models, we can compute the linear regression function by using the Q13 previous three sample experience sample point, and then we can calculate the confidence of these regression functions by compute the difference between the estimated result and actual running time. And then we have defined a square function that can balance between the total running time and punishment and penalty to get the optimal value that for the next query to generate. So in this model, we shows that if we choose R4, the range of the query Q4 as 9 days, it can best optimize get a mathematically better performance. So we choose the 9-day range predicate for Q4, and then suppose the Q4 runs 3 seconds and finish at 6.8. At this moment, the query mini query executor will utilize the 9-day and 3-second runtime statistics to the estimator. So estimator will update his linear regression and confidence models to calculate and to update models. So and then we can using this model again to the new data with the new data to predict the to better predict the range of the Q5. This progress will be runs for every mini query until the entire query has been finished. So as an example, we have collected 100 million tweets, real tweets, through the Twitter streaming API, which have 90 GB of data. The time range from November 2016 to January 2017. We are using a 3DB 0.92 version and then we create the index on the create field and the inverted index on the text field. We run the experiment on a single machine which consists of 4 cores and 16 GB of memories. And the middleware is also also runs on this machine. So our test query is simple. We just count the by state aggregation for the number of tweets, mention different keywords. And then we compare the number of mini queries and total running times for 2 different batch of queries. We can we differentiate workload with a high selective workload and low selective workload. The high selective workload will return less result, and the low selective will return more result, will tend to run longer than the high selective queries. And then we compare 3 different schedules. The NS is non-slicing schedule, which doesn't do slicing at all, and the FL is a fixed length schedule. It will always split the query into 60 mini queries, and drum is a slicing adaptive slicing method we proposed earlier. You can see in terms of number of mini queries, the non-slicing will only issue 1 query, and for the fixed length, no matter how selective the query it is, it will just use the unified result. And for drum, it can adaptively change the number of results that's sent to the database. And then, in terms of time, for the high selective queries, FL doesn't change so much. So, in terms of total running time, query slicing doesn't actually give much overhead to the solving query to complete the result to complete the result. And then in terms of delays, the fixed length works well for the high selective queries, but there's no uniform a fixed length that can apply for all the case. So for the low select case, the fixed length scheduling will tend to uh, have have to select to tend to cause more delays because each of the mini query may run longer than expected. The drum framework, no matter for all the high select keys and low selected keys, can pick the can pick can adaptively picks the number of queries need to run, and correspondingly, the cost of the is cost of the drum is pretty consistent, no matter agnostic to the, for both high selective and low selective keys. So conclusions, we mm, study and well define a problem of query slicing to answer the big queries responsibly, and we proposed a solution as drum framework, which can slicing on the dimension adaptively. So this screenshot or animation shows the user experience of the drum framework. As you can see, user can get the earliest response at as fast as possible, and then it can keep receiving the more result in a regular pace, so that the user can make decision more quickly. At the same time, the UI interface is much more responsive. Finally, let's just introduce the Cloudberry. I just want to have one word to introduce our Cloudberry project. So Cloudberry project is a generic middleware which we want to achieve the real-time analytics and visualization of big data. The weapons we have is automatically using materialized views, answering queries, and also using query slicing to speed up the interactiveness of the visualization front end. And then as a generic middleware, we support different front end, and we have included different database connectors to connect to different databases. And you're welcome to check this website to have a try. So thank you. So